Hello everyone and welcome to Coders of Pune. Today we're diving into Unit 6 of Computational Statistics, focusing on statistical modeling. This unit is a cornerstone for anyone pursuing AIML honors, as it introduces the essential tools and techniques for building robust machine learning models. Throughout this video we'll explore foundational concepts, practical methods, and real-world applications that will empower you to understand, predict, and infer relationships from data. Whether you're new to statistical modeling or looking to deepen your expertise, this unit will provide the clarity and confidence you need to tackle advanced machine learning challenges. Let's get started on this exciting journey together. Statistical modeling is all about creating simplified mathematical representations of real-world processes. These models help us understand, describe, predict, and infer relationships between different variables. By making informed assumptions about how data is distributed and how variables interact, we can translate these relationships into mathematical equations or algorithms. The ultimate goal is to capture the underlying structure and patterns within data, allowing us to make sense of complex phenomena and make informed decisions. Whether you're analyzing trends, forecasting outcomes, or testing hypotheses, statistical modeling provides the foundation for extracting meaningful insights from data. Linear regression is one of the most fundamental tools in statistical modeling. Its main purpose is to establish a linear relationship between a dependent variable, the outcome we want to predict, and one or more independent variables, which are the predictors. The model finds the best fit straight line, or hyperplane in higher dimensions, that minimizes the squared differences between observed and predicted values. This line helps us predict new outcomes, understand the strength and direction of relationships, and infer how changes in predictors impact the outcome. Remember, the term linear refers to both the linearity in parameters and often the relationship itself. If the true relationship is nonlinear, linear regression may not perform well, highlighting the need for more advanced techniques. Correlation coefficient, usually denoted as R, measures the strength and direction of a linear relationship between two variables. It ranges from -1 to +1. Values closer to +1 or -1 indicate a strong linear relationship, while values near 0 suggest a weak or no linear relationship. A positive correlation means both variables move together, while a negative correlation means they move in opposite directions. If R is around 0, there's no linear relationship, though a nonlinear relationship might still exist. Correlation coefficients are crucial for understanding how variables are connected, but remember, correlation does not imply causation. And correlation is a non-parametric measure that evaluates the relationship between two variables based on their ranks rather than their actual values. This approach is especially useful when data doesn't meet the assumptions required for parametric tests, such as linearity or normality, or when outliers are present. Instead of focusing on the magnitude of change, rank correlation assesses the consistency of ordering between two sets of ranks. The most common types are Spearman's rank-order correlation and Kendall's tau rank correlation is ideal for ordinal data, monotonic relationships, and situations where outliers might distort traditional correlation measures. This image illustrates the concept of correlation between two variables, x and y. The first graph shows a positive correlation, where an increase in x corresponds to an increase in y with a correlation coefficient R0. The middle graph depicts zero correlation, indicating no linear relationship between x and y. R equals 0. The last graph represents a negative correlation, where an increase in x is associated with a decrease in y. R0. Rank correlation shines when the relationship between variables is monotonic but not necessarily linear. It's particularly valuable with ordinal data, such as ratings or preferences, and when outliers could skew results. If your data violates the assumptions of Pearson correlation, like normality, rank correlation provides a robust alternative. By focusing on the order of data rather than the actual values, it offers a more resilient measure of association, especially in real-world scenarios where data is messy or doesn't fit traditional models. Residual error are more than just leftover errors. They're a window into your model's strengths and weaknesses. By examining residual errors, you can assess how well your model fits the data, check if key assumptions are met, and spot outliers or influential points. If residual errors show systematic patterns, it might mean important variables are missing or the model's form isn't quite right. Large residuals can highlight data points that deserve closer scrutiny. Ultimately, analyzing residuals is a crucial step in refining and improving your statistical models. Mean squared error, or MSE, is a key metric in regression analysis. It measures the average squared difference between predicted and actual values, giving us a sense of how well our model is performing. MSE heavily penalizes larger errors, making it sensitive to outliers. The units of MSE are the square of the dependent variable's units, which can make interpretation tricky, but a lower MSE always indicates a better fit. In machine learning, MSE is often used as a loss function to optimize model parameters during training. MSE stands out for several reasons. First, it magnifies larger errors, making models sensitive to outliers. Second, its units are squared, which can complicate direct interpretation. Third, a lower MSE signals a better model fit, while a higher MSE means the model's predictions deviate more from actual values. Finally, MSE is widely used as an optimization objective in machine learning, guiding algorithms to find the best parameters by minimizing prediction error. Beyond simple linear regression, advanced models help us tackle more complex relationships. Multiple linear regression models the relationship between a dependent variable and two or more independent variables. Polynomial regression allows us to fit curves to data, capturing nonlinear trends. Logistic regression, despite its name, is used for classification tasks, predicting the probability of binary outcomes. Gradient descent is a powerful optimization technique that helps us find the best model parameters by minimizing a cost function. Each of these methods expands our toolkit for modeling real-world data. Multilinear regression, also known as multiple linear regression, is a powerful technique for modeling the linear association between a dependent variable and two or more independent variables. By accommodating multiple predictors, MLR identifies the optimal best fit hyperplane in a multidimensional space. This approach minimizes the squared differences between observed and predicted values, providing a comprehensive understanding of how several factors jointly influence the outcome. MLR is widely used in fields like economics, finance, marketing, healthcare, and social sciences. General equation for multilinear regression is y equals beta 0 plus beta 1x1 plus beta 2x2 plus beta nxn plus epsilon. Here y is the dependent variable, beta 0 is the intercept, beta 1 to beta n are the coefficients for each independent variable, x1 to xn are the predictors, and epsilon is the error term. Each coefficient represents the expected change in y for a 1-unit increase in the corresponding x, holding other variables constant. This structure allows us to isolate the effect of each predictor, making MLR a versatile tool for multivariate analysis. Multiple linear regression finds applications in a variety of fields. In economics, it's used to predict GDP based on factors like inflation and unemployment. In finance, it helps forecast stock prices using company earnings and market trends. Marketing analysts use it to assess the impact of advertising spend and pricing on sales. Healthcare professionals predict patient outcomes based on demographics and medical history, while social scientists explore factors influencing education or voting behavior. The ability to handle multiple predictors makes MLR invaluable for complex, real-world problems. Multiple linear regression offers several advantages. It provides a comprehensive understanding of relationships between multiple variables, allowing for more accurate predictions than simple linear regression when several factors are involved. The coefficients are relatively straightforward to interpret, especially when considering the influence of each variable independently. This makes MLR a go-to method for many practical modeling scenarios where multiple influences must be considered. Despite its strengths, multiple linear regression has some limitations. It's sensitive to outliers and influential data points which can distort results. The model assumes linearity, which may not always hold true in real-world data. Multicollinearity, when predictors are highly correlated, can make interpretation challenging. Finally, MLR requires several statistical assumptions to be met for valid inference, such as independence and normality of error. Polynomial features are a feature engineering technique that extends linear models to capture nonlinear relationships. By creating new features that are powers of the existing independent variables, polynomial regression can fit curves to data that a straight line cannot. For example, if you have a variable x, polynomial features would include x2, x3, and so on. This approach is especially useful for modeling real-world phenomena that exhibit curves or bends, enhancing the flexibility and accuracy of regression models. Polynomial features are ideal for modeling nonlinear relationships, curve fitting, and regression analysis where a simple linear model falls short. They're used in scientific and engineering applications to approximate complex functions and in feature engineering to create more expressive variables. By capturing the curvature in data, polynomial features can significantly improve model accuracy, especially when the underlying relationship is inherently nonlinear. Main advantage of polynomial features is their ability to fit nonlinear data using linear models, often improving accuracy. However, they can lead to overfitting if the polynomial degree is too high, especially with limited data. This increases model complexity and can make interpretation more challenging. Additionally, polynomial models are sensitive to outliers, which can disproportionately influence the curve. Gradient descent is a cornerstone optimization algorithm in machine learning. Its goal is to minimize a cost function by iteratively adjusting model parameters in the direction of steepest descent, as indicated by the negative gradient. Starting with initial parameter values, the algorithm calculates the gradient, updates the parameters, and repeats this process until it converges to a minimum. Gradient descent is widely used to train models by finding the set of parameters that minimize prediction error. The process begins with arbitrary initial parameters. The algorithm then computes the gradient of the cost function with respect to each parameter, indicating the direction of steepest increase. To minimize the cost, parameters are updated by subtracting a fraction of the gradient, controlled by the learning rate. This cycle repeats until the cost function stabilizes, signaling convergence. The learning rate is crucial. Too large and the algorithm may overshoot, too small and convergence is slow. Gradient descent revolves around a few key concepts. The cost function or loss function quantifies prediction error and is what the algorithm seeks to minimize. The learning rate determines the size of each update step. If the cost function has multiple values, the algorithm may find a local minimum rather than the global minimum. Despite its simplicity, gradient descent is powerful and forms the backbone of many machine learning algorithms. Gradient descent is widely applicable and relatively simple to implement. However, it's sensitive to the choice of learning rate and can get stuck in local minima, especially with complex cost functions. For very large datasets, calculating the gradient for all data points can be slow, but this is addressed by variants like stochastic and mini-batch gradient descent. There are three main variants of gradient descent: batch gradient descent, stochastic gradient descent (SGD), and mini-batch gradient descent. Batch gradient descent uses the entire dataset for each update, making it stable but slow for large datasets. SGD updates parameters using a single randomly chosen data point, resulting in faster but noisier convergence. Mini-batch gradient descent strikes a balance by updating parameters using small batches of data, combining speed and stability. Batch gradient descent (BGD) and stochastic gradient descent (SGD) differences. BGD uses the entire dataset to compute the gradient and update parameters. SGD uses a single, randomly selected data point for each update. BGD is computationally expensive and has a high memory requirement. SGD is much faster and requires less memory, making it ideal for large datasets. BGD updates parameters less frequently, leading to a smooth, stable convergence path. SGD updates parameters very frequently, causing a noisy and zigzagging convergence. Noise in SGD can help it escape local minima and find a better solution. BGD is best for smaller datasets where high precision is required. SGD is preferred for large datasets and online learning where speed is key. Mini-batch gradient descent combines the best of both worlds by updating parameters using small batches of data. This approach offers a good balance between the stability of batch updates and the speed of stochastic updates. Mini-batch methods are widely used in deep learning and large-scale machine learning, as they efficiently utilize computational resources and often lead to faster convergence. Logistic regression is a statistical model designed for binary classification problems. It predicts the probability that a categorical dependent variable takes on one of two possible outcomes, such as yes, no, or pass-fail. Despite its name, logistic regression is a classification algorithm, not a regression algorithm. It uses the logistic or sigmoid function to transform outputs into probabilities between 0 and 1, which are then mapped to class label. Core of logistic regression is the sigmoid function, which squashes any real-valued input into a value between 0 and 1, representing the probability of belonging to a particular class. A threshold, usually 0.5, is applied to classify outcomes. The model uses a log-loss cost function, which it minimizes using optimization algorithms like gradient descent. Logistic regression is widely used for medical diagnosis, spam detection, customer churn prediction, and credit scoring. Logistic regression is applied in a variety of fields. In healthcare, it predicts the presence or absence of diseases based on symptoms and test results. In email filtering, it classifies messages as spam or not spam. Businesses use it to predict customer churn or assess credit risk. In marketing, it helps determine the likelihood of a customer clicking on an advertisement. Its simplicity and interpretability make it a popular choice for binary classification tasks. Logistic regression is easy to understand and implement. Its coefficients reveal the influence of each variable, making interpretation straightforward. The model is computationally efficient and trains quickly, even on large datasets. It provides probability scores which are useful for ranking and decision-making. Logistic regression is also robust to noise when dealing with binary outcomes, especially if relationships are simple. Despite its strengths, logistic regression has limitations. It assumes a linear relationship between independent variables and the log odds of the outcome, which may not always hold. The model is primarily for binary outcomes. Multi-class problems require extensions. Logistic regression is sensitive to outliers and may need extensive feature engineering for complex nonlinear relationships. For highly nonlinear decision boundaries, more advanced algorithms may perform better. Linear regression predicts a continuous output like price or temperature. Logistic regression predicts the probability of a categorical outcome, such as yes, no, or true, false. Linear regression's output can range from negative to positive infinity. Logistic regression's output is constrained to a probability between 0 and 1. Linear regression is evaluated using mean-squared error, (MSE). Logistic regression uses log-loss or cross-entropy to measure its performance. Linear regression's typical use cases include predicting house prices or sales. Logistic regression is used for classification tasks like spam detection or disease prediction. The underlying function in linear regression is a simple linear equation, whereas logistic regression applies the logistic sigmoid function to the linear combination of inputs to map the output to a probability. Linear regression assumes the errors are normally distributed Gaussian, which is crucial for statistical inference. In contrast, logistic regression assumes the errors follow a binomial distribution. Bayesian statistics is a paradigm that treats probability as a measure of belief or confidence, rather than just a long-run frequency. Unlike frequentist statistics, Bayesian methods incorporate prior knowledge or beliefs about parameters and update these beliefs as new data becomes available. This approach produces a posterior probability distribution, reflecting our refined understanding after considering the evidence. Bayesian statistics is especially powerful for sequential learning and decision-making under uncertainty. Bayes' theorem is the mathematical foundation of Bayesian statistics. It calculates the conditional probability of an event by updating a prior belief with new evidence. The theorem combines the prior probability, the likelihood of observing the data given the hypothesis, and the marginal likelihood to produce the posterior probability. This iterative process of updating beliefs makes Bayesian statistics a dynamic and powerful tool for inference. Let's break down Bayes' theorem. Mathematically, the probability of a given B equals the probability of B given A, multiplied by the probability of A, all divided by the probability of B. The posterior probability, P of a given B, is what we want to calculate. It's the probability of hypothesis A given evidence B. The likelihood, P of B given A, tells us how probable the evidence is if the hypothesis is true. The prior, P of A, reflects our initial belief about the hypothesis. The marginal likelihood, P of B, normalizes the result so that probabilities sum to 1. This structure allows us to continuously refine our beliefs as new data arrives. Bayesian approach starts with an initial belief or prior. As new data is observed, we evaluate how well the hypothesis explains the data, the likelihood. We then update our prior belief to posterior belief, weighing the prior against the evidence. This process repeats as more data becomes available, making Bayesian statistics ideal for learning in dynamic environments where information is constantly evolving. Monte Carlo method is a class of computational algorithms that use repeated random sampling to obtain numerical results. Instead of performing a deterministic calculation, Monte Carlo simulates a process many times, drawing random numbers to represent uncertain variables. The results are aggregated to estimate numerical values, making this approach especially useful for problems that are too complex to solve analytically. Typical Monte Carlo simulation involves several steps. First, define the domain of possible inputs. Next, generate random inputs from a specified probability distribution. For each set of inputs, perform a deterministic computation to get an outcome. Aggregate the results from all simulations to estimate the overall output. Finally, calculate statistics like the mean or variance to understand the solution. This process is intuitive and flexible, making Monte Carlo methods widely applicable. Monte Carlo methods excel at handling complex, high-dimensional, and nonlinear problems that are intractable with analytical methods. They're flexible and can be applied across fields like physics, finance, and engineering. The approach provides a distribution of possible outcomes, offering a deeper understanding of uncertainty and risk. Monte Carlo simulations are also highly parallelizable, making them efficient for large-scale problems. Despite its strengths, the Monte Carlo method has limitations. It requires a large number of simulations for accurate results, which can be computationally expensive and time-consuming. The convergence rate is slow, and defining accurate input distributions can be challenging. The quality of random number generators is crucial, as poor randomness can introduce bias. Finally, Monte Carlo is not suitable for problems with simple analytical solutions. Monte Carlo methods are used in a variety of real-world scenarios. In finance, they estimate the value of complex derivatives and assess portfolio risk. In engineering and science, they simulate particle interactions, drug discovery, and environmental modeling. Operations research uses Monte Carlo for project management and supply chain optimization. In artificial intelligence, Monte Carlo tree search powers game-playing algorithms, while Bayesian inference relies on Monte Carlo for complex probability calculations. Machine learning, Monte Carlo methods are used for reinforcement learning, where algorithms simulate possible actions and outcomes to make decisions. They're also key in Bayesian inference, helping approximate posterior distributions when analytical solutions are intractable. Monte Carlo simulations are invaluable for hypothesis testing and constructing confidence intervals in complex statistical models. Monte Carlo methods provide a powerful way to tackle uncertainty and complexity in statistical modeling. By simulating processes repeatedly and aggregating results, they offer insights that are often unattainable through traditional analytical methods. While computationally demanding, their flexibility and ability to handle high-dimensional problems make them a staple in modern data science and machine learning. In this unit, we explored the foundations of statistical modeling, from linear and multiple regression to advanced techniques like polynomial features, gradient descent, and logistic regression. We delved into the world of Bayesian statistics and the Monte Carlo method, understanding how these tools help us model, predict, and make decisions under uncertainty. By mastering these concepts, you're well equipped to build robust machine learning models and tackle real-world data challenges with confidence. That concludes Unit 6 on statistical modeling. The topics we've discussed today, like linear regression, gradient descent, and Bayes' theorem, are the building blocks of many machine learning algorithms. This is the final unit of the computational statistics subject for this semester. I encourage you to experiment with these concepts by applying them to your own datasets. Practice is key to mastering these techniques. Thank you for watching and stay tuned with Coders of Pune for our next AIML honors subject in the coming semester.